Welcome back to ECE 320A. The noise level indicates that something is right around the corner. A slight break maybe in action, but not yet. Not for you, not today. We're going to have a good time talking about Bode plots. That's what we're hoping to accomplish today. Homework 9 deals with Bode plots, and if you have some extra time in the airport or sometime, you might start that assignment. It's due a week from Thursday, whatever is happening on Thursday. But it's due on the 5th. Your final exam is a few weeks from today. Not very many, about 3 weeks from today. Less or take away 2 hours. So make sure that you get up a little bit earlier if this is your first class of the day normally. I don't think it is, but if it was, make sure you are here at 10:30 a.m. on that Tuesday morning, the 17th of December. As I said, today what I want to do is work through a Bode plot example, and actually I'm going to do that in several steps. The first step is to write down a word description. So if you can't sketch it, at least you can write it down, is what I would like to think. Then we will talk about connecting all of our pieces. Last time I think we sketched all the individual pieces and never really put them together. We'll try to put those together so that you have the complete or the actual Bode plot for your system. Then we'll have a quiz on the Bode plot and some additional questions. I don't think we're going to get there, but if you want to read ahead, chapters 14 and 15 is where we are headed with filtering. Chapter 14 is passive filters, which means RLCs interconnected in a way to produce filtering behavior. And chapter 15 is active filters. Now we have op amps that we can put in there. We've energized circuit elements. We have those powered up, and now we can put components around those to produce certain filtering behavior. And the filters that we should be comfortable with are low pass, high pass, band pass, and band reject. Those shapes we should be comfortable with, and you actually should be able to build those up on a, let's say, a frequency response diagram. Now you can extract from that the transfer function. So you could do filter design based on what we've talked about, especially after today's class. Let's then get started with a Bode plot. And suppose that somebody gives you a transfer function, capital H of S, 10,000 S plus 0.1 over S times S plus 100. Definition or terminology, what structure or form is that transfer function written in right now? Pole zero form. The factors are written so that you can easily identify where your zeros are at and your poles are at. This is what we call the pole zero form, and that's ideal for sketching the S-domain poles and zeros. Is this the structure we need to sketch a Bode plot? No, you want to convert all of those constants in your factors to be ones. You need to factor those pole and zero values out and put those underneath your S's to produce a time constant form, which is the reciprocal of those poles and zeros. So let's now do that. Now if we write this in time constant form, we're going to factor out all of those coefficients, and here we only have linear factors to worry about, so we don't have to worry about these quadratic factors. The pole at the origin, it's fine to leave by itself. but then we have the pole at 100 that we factor out, and now we have our time constant form if we simply combine all of those constants out in front. And we can see that the 0.1 will get rid of one of those zeros, and the 100 downstairs will get rid of two of those, and so we really end up with our transfer function h of s being 10, s over 0.1 plus 1 over s over 100 plus 1, and this is now in the form that we need to be sketching or drawing the Bode plot. This is now in time constant form. We have a pole at 100. What's its time constant? It's the value that's multiplying that s in its factor. So it's 1 over 100. It's 0.01. It's 1 or 10 milliseconds. That's the time constant associated with that pole at s equal minus 100, if somebody asks you. And then how long would you have to wait for your transient to be gone in this circuit? 5 of those. So 5 times that 0.01, or 50 milliseconds. Not very long you would have to wait. You don't have to worry about the zeros when you're dealing with time constants in terms of transients. Some of you on the test were looking at the zeros location and using that to determine your slowest time constant or your longest time constant. What we want to do, though, is we want to walk up the imaginary axis to sketch the Bode plot, which means now instead of looking at this transfer function as a function of s, we substitute or replace all of those s's with j omegas. So that now we have 10, then we have j omega over 0.1 plus 1 all over j omega and j omega over 100 plus 1. Another common concern on the exam is what's the angle associated with j? Just j. What's the angle of j? 90. Some of you forgot that. It was in the numerator on the exam. You had a j something, or you had an s, and people forgot to incorporate that j in one of the problems. I can't even remember what it was. All right. Now let's look at how we might create or produce a word description of this Bode plot. Is it clear the factors that we now have that are going to go together to create the Bode plot? We have a constant, that's 10. We have a pole at the origin, that's the j omega. We have a linear zero, or a real zero at s equal to minus 0.1, and we have a real pole at s equal minus 100. Those are our 4 terms that we now need to describe in this word description, and then we'll sketch those in a Bode plot. We'll do it in that order. Let's say that the first one that we will talk about is the constant. Either the constant term or the constant factor. In this case, it's 10, and we have 2 pieces for each of these terms. We have a magnitude piece and a phase piece. For the magnitude piece, we're looking at 20 times the log, and that's base 10, I may not always write that, of the absolute value of the gain, which in this case was positive, so I'll just write down absolute, or log of 10. Log of 10 is 1, so now we have 20 dB, and that is always on. That gain is constant across all frequencies. That's not fluctuating. That's for all omega. What's the phase of this constant number 10? What's the angle of 10? And that's not a function of frequency either. That's for all frequencies. And we're done. That's the first term. Let's now look at the second term, which let's go ahead and look at these in terms of when they occur or need to be considered as we're moving from low frequencies, 0.001 or 10 to the minus 7, all the way up to high frequencies, let's say 10 to the 9. We don't go that far, but that's why we do it on a logarithmic scale so that we can consider a large frequency range or interval. Here, let's look at the single pole at the origin. That's our next term. For the single pole at the origin, again, we have the two pieces that we will sketch two different plots for. We have the magnitude piece and the phase piece. The magnitude piece, if I look at this pole at the origin, what do I know about that particular term as a function of frequency omega? Where is it located? It's a pole, so it's downstairs. That means it has a negative slope. Does it ever break? Is it flat and then breaks? Do you have a constant term added to that? No. This one is always sloping. It never breaks. It never starts sloping. It's always sloping. It doesn't go flat and then break. It's always on in terms of a slope. This one then, if we wanted to describe the magnitude, I would say it's a straight line. And that straight line has a slope, and it's only one, and it's a pole. So we know each factor gives us 20 dB per decade, but since it's a pole, it's negative. So this has a slope equal to minus 20 dB per decade. Now that we could locate anywhere, but we can't locate it anywhere, so we need to tell you where to pin it on the diagram, and that's what this crossing point says. It crosses this 0 dB line at what frequency? So 0 dB corresponds to a gain of 1. The magnitude of j omega, we can forget the j, it has a value of 1. So now we're looking at the magnitude of omega. We want to know when is that equal to 1, at what frequency? Well, it's at 1 radian per second. So this is going to go through 0 dB right there at 1 radian per second. It's not going to break there. It's going to just pass through there because its slope is always minus 20 dB per decade. So its value is really big at low frequencies. Its value is really small at high frequencies. That's its magnitude. So it's always on, it's always sloping, it's never going to break. That's important because a lot of people want it to break at 1. That's just where we're locating it or using it to locate. Then what's the phase? That one's easy to sketch. It's minus 90 because it's downstairs. That single factor gives you 90 degrees, and since it's a pole, it's minus 90, and it never changes. It never goes up or down or has a slope. It's flat at minus 90 for all frequencies. That's the word description for the second piece, which is this pole at the origin. The first piece was that constant term. Now, if we're working our way from small frequencies to high frequencies, which factor should we consider next? The zero's occurring at a smaller frequency, isn't it? It's occurring at omega equal to 0.1 versus the pole, which is occurring at omega equal to 100. So this is now the next factor that we'll consider. That's the zero, the single zero, or the linear zero. Let's say that's now factor 3. That's this single zero at S equal to minus 0.1 radian per second. Now we have to describe the magnitude of this. At really low frequencies, what's its magnitude, this factor? If you go back and you look at that factor that I've circled or enclosed with 3, if I put in a really small frequency, and what's a small frequency for this factor? Frequency depends on the polar zero factor. If I said, what's a small frequency for term number 3, what would you tell me? 0. That's really small, isn't it? DC. You could say DC. But in terms of getting close to its break, you could say, well, a decade away from that break could be considered small. So DC all the way up to 0.01 would be pretty small for that term. Is that okay? But DC is fine for this one. But if I said at low frequencies, for that factor, low frequencies, you might say, oh, that's anything less than a decade before it breaks. That's maybe 0.01 radians per second. Is that clear? Meaning the magnitude is going to be 0 dB or flat until we get right to where that 0 breaks. And it breaks at its 0 location, which is 0.1 radians per second. And at that point, it now breaks. And now it starts to have a slope. And what's the slope of a 0 factor? It's in the numerator, it's upstairs, so it's plus 20 dB per decade. Once it starts sloping, do we ever have to turn off that slope? In the magnitude, no. Once it turns on, it's always on. The phase is a different beast. The phase only is sloping over a 2-decade interval, and that 2-decade interval is centered right at the break frequency. And the way that I like to describe that is I say, oh, the phase is 0 degrees when we are a decade in front of the break. So that's a 1/10 of the break, which in this case is 10 to the minus 2, or 0.01 radians per second. What's the angle right at the break? If I went back to factor 3 and I plugged in omega equal to the break, 0.1, I now have a j plus 1, or 1 plus j. That has an equal horizontal, equal vertical. The angle, 45 degrees. And it's upstairs because it's in the numerator. So now at omega equal to 0.1, the break, it's at 45 degrees. Then in our straight line approximation sketching, we say the next frequency of interest is a decade beyond the break, which is 10 times 0.1. And now we just assume that it's completely maxed out in terms of its phase contribution. So now you could say, oh, omega is huge compared to 0.1. So now if I'm looking up, if I'm standing at 0.1, which is pretty close to the imaginary axis, right? And now I look up the imaginary axis, what's my angle going to be from that point up? 90 degrees is as much as that particular term can contribute. So this is now going to be 90 degrees in our straight line approximation at 1 radian per second. And that's now my word description for the third term. Finally, we have our fourth term, which is this single pole at minus 100 radians per second. And once you understand this approach, it's pretty easy to start writing. Oh, I know it's 0 dB until when? Right at the break, which is 100 radians per second. At that point, it now experiences a break. And what's the slope? It's a pole, so it's now minus 20 dB per decade. See how you could quickly just write this text down for a word description? What's the phase of this factor? So now I have my Goldilocks, right? I have 3 frequencies. It's 0 degrees, a decade before the break, or in this case, 10 radians per second. Right at the break, it's a pole factor. Our real part and our imaginary part are equal at that frequency, and that's now minus 45 degrees. And the most that that single factor can contribute in terms of phase is minus 90 degrees, and we just go ahead and approximate that to say, oh, a decade above the break, or at 1,000 radians per second is where that experiences minus 90 degrees, and from that point onward, it's minus 90 degrees. So the phases, you have to worry about turning on the slope and turning off the slope, starting the slope and stopping it. For the magnitudes, once it starts sloping, you don't have to worry about it. You can just keep going. Now we can sketch it. And we're going to sketch 2 different curves. We have the magnitude curve and the phase curve. Now if I draw my frequency axis, this is going to be on a logarithmic scale. What points should I include on that frequency axis? What frequency should I start with? And now that's why we've written this down. We're looking for large and small. If we scroll down, the constant term is constant for all frequencies. That really doesn't impact our frequency decision. Our single pole at the origin says, oh, omega equal 1 is a nice frequency to be worried about, because that's where it's going to cross 0 dB, potentially. The 0, its smallest frequency is 10 to the minus 2, 0.01 because of the phase. Its biggest one is 1. And if we look at the pole, its smallest is 10. So now we're going from 0.01 up to 1,000. So if we just hit those 2 extremes, we would be plotting our frequency axis from 10 to the minus 2 up to 10 to the third, or 0.01 up to 1,000. But let's go ahead and expand that a decade on either side. That's now going to give me my frequency axis. I said I needed to be at least 10 to the minus 2. Let's say this is now going to go back 10 to the minus 3. And then here's 10 to the minus 1. Here's 10 to the 0, which is 1. There's 10 to the 1. Uh-oh, I'm going to run out of space. 10 to the 2. 10 to the 3. This is radians per second. And if you go to the bookstore and ask for semi-log paper, they'll ask you how many cycles. I know the customer service over there, they know their log paper, semi-log paper. They'll say, do you want semi-log or log-log? And you'll go semi-log, and I need 1, 2, 3, 4, 5, 6, maybe even 7 cycles. They don't sell it very often in that variety. Usually it's 4 or 5 cycles. How many have gone and purchased semi-log paper at the bookstore? We used to have to do that, okay? We had the old school. We'd get out the ruler, the straight edge, have to be drawing this. You can now just sketch it across, but you have to realize that you're doing a log scale. So if you needed to go to, let's say 2, that would be between which of these two numbers? If I needed to go to 2 radians per second, where would I be traveling? Or where would I locate myself? 10 to the 0 and 10 to the 1. And how far between those am I if I'm at 2? You're looking at log 2, so you're 30% of the way between those. It's not this normal breaking up in rectangular grids. Now you have a logarithmic. So you would be 30% of your way between 1 and 10 if you were at 2. Okay? All right. Where are we? Now let's sketch these. We have our constant. So for the magnitude, I can simply introduce there's term number 1, 20 dB, due to the constant. Then the pole at the origin, term number 2 in terms of magnitude, that's a straight line. It's always sloping down, and it's passing through 0 dB. Here is 0 dB at omega equal to 1. So if it's sloping, it's going to be minus 20 at 10, and it's going to be plus 20 at 0.1. It's going to be at 40 here, and now I have to make sure my sketch is somewhat, well, I can, I guess, adjust my straight line to be a little crooked if I need to, but that's now my term, magnitude term, associated with the pole at the origin. So everybody see how that was drawn. It never was flat, it's always sloping. And if you have a 0 at the origin, it's always sloping, and it's going to go up at plus 20 dB per decade, and it's going to cross the same point, 0 dB at omega equal to 1. The next term, magnitude-wise, is the 0. It's flat. It's not contributing any magnitude until you reach 0.1, which is right here, and then it's going to go down at 20 dB per decade. So now this one, and those should be parallel lines. This is supposed to be, are you guys asleep? I am. What did I just do? I'm thinking about turkey or pi or something. That was a 0, wasn't it? I need to go up. Starting this is okay. I got the first half right, but I lost 20 points out of the 10 on the second half. So this is now going up at, you guys laugh. There's my 0, right? That's term number 3. Where's my last term? That's my pole at 100. It's going to be flat until I reach 100, which is over here, and then it goes down 20, 40, etc. So there is my last term's contribution. If you sketch the Bode plot in MATLAB, it's not going to give you all of these 4 different curves. It's just going to give you the result, magnitude. And we can do that by adding all of these up piece for piece. That's why we're doing it in dB. Now we can add all of these different terms linearly on this particular plot. Meaning, what I like to do a lot of times is I like to go back before anything has broken, before a pole or a 0 that has started to be active, and I go far enough to the left. Maybe I go back to 10 to the minus 2 and I say, okay, what is the gain at that particular frequency? Right at 10 to the minus 2, what should be my magnitude? What's active? I have a constant and I have a 0. I'm sorry, a pole at the origin. Those 2 terms are active at this particular frequency, 0.01, 10 to the minus 2. And now I need to add those up. I have 20 that's coming to me from the constant, and I have 40 coming from the pole at the origin. Those 2 sum to 60, meaning their sum would give me the net result up here at 60 dB. Is everybody seeing that? What am I going to have as far as a contribution at 10 to the minus 1? I have 20 from the constant. How much do I have from the pole? 20. So I have 20 and 20, that's 40. Now I'm right here. And that pole is always on. So now I'm coming down. That's supposed to be a straight line. But now, if I'm looking at what's happening, something magic happens right here. Now I get a change in slope because of that 0. That 0 introduces a slope change. I'm coming down in the red curve. That's my total. That's my complete Bode plot curve of the magnitude, the red curve. I'm coming down at 20 dB per decade. Then what do? I experience a change in slope of plus 20. Minus 20 plus 20. Now I have 0 slope. My slope now is flat. And I know where that is. That's supposed to be at 40 dB. And I keep going flat until what? Until I see another slope change. And that's going to happen right out here at 100. So I continue to be flat until I reach the next break, which could have been a 0 or a pole, and now I need to say, okay, now what's my slope? I have a 0, I have a pole, and I have a second pole. Negative 20. Down, right? So if I'm 40 here, then at the next decade, I better be at 20. And at the next decade, I better be at 0. And I would just keep sloping at that slope for all frequencies thereafter. And that red curve is then the total. Is it clear where that came from and how that we sketched it? And this is what you would see produced from MATLAB. It would generate that red curve, and it would be more accurate. It would have more accurate values at each of these little kinks. This is just a straight line approximation. Questions on where that came from? You're going to have to know how to sketch these. Yes? Why is the line flat? So the red line is flat because I have my pole at the origin, that number 2 line, that's producing minus 20 dB. And the number 3 line at that point is producing plus 20 dB. So now I have minus 20 plus 20, they cancel in slope, and I'm now not sloping because I have two factors that are both active at that point. One's down, one's up, so now I'm flat. That's why I'm not sloping between, and I could ask this on the final. I could say, where is the magnitude plot flat in slope? Or where does the magnitude plot have a 0 dB per decade slope? Between what frequencies? And you would say 10 to the minus 1 or 0.1 up to 100. I could say, what's the slope at high frequencies for this system? And you would say, in magnitude, the magnitude slope, I'd have to say magnitude or phase, but the magnitude slope at high frequencies, you're rolling off at 20 dB per decade at high frequencies. High frequencies in this particular example means above 100. I could say, what's the slope at low frequencies? And you would go, what do you mean by low frequencies? And I would say, I cannot answer that. That's part of the question. What is low frequency in this example? It's less than where anything breaks, isn't it? In this case, it's 10 to the minus 2 or 10 to the minus 3. What's the slope there? It's minus 20 dB per decade. I could ask you, what's the magnitude at 1 radian per second? What's the magnitude in dB from your straight line approximation? And you would say 40 dB. See how I could ask a large number of questions just from one plot? All right, let's now do the phase curve. Is it clear how to sketch that curve and how to build it up from the different pieces? It needs to be. If it's not, come see me in office hours the day before break. Somebody was asking me yesterday if I was going to be in office hours. I said, yes, sir. Whoops, I just gave half the answer away, didn't I? It was a student in this class. All right, where was this? This was 10 to the minus 3, and you want to typically try to align your two different plots so that it's clear what the magnitude and the phase are doing together. This is now the angle of H, of j omega, and this curve or axis is radians per second. Now we go back to our terms, and with this word description, it should just jump out at you how to sketch this. I know you're saying, why do I have to do so much to sketch this? Well, before you get really comfortable with it, it's kind of nice sometimes to just write it down, and then you don't have to think too hard or keep track of a lot. The constant term, don't need to adjust the sketch, do I? It's 0 degrees. the pole at the origin. That one is just going to be a constant flat line at minus 90 degrees. So that's going to give me this. If this is now 0 degrees and this is minus 90 degrees, this is due to the second term. Now, these poles and zeros, these linear factors, these are a little bit more interesting, and the adding them up is a little bit more interesting because they turn on and turn off in their slope. But this one, just look at those 3 points and plot those numbers. At 10 to the minus 2, I'm going to start changing. And at 10 to the minus, or at 10 to the 0, 2 decades beyond is when I'm going to quit changing. And at that point, I'm going to be at 90 degrees because it was a 0. This is now, and I was 0 degrees before that if I wanted to draw that. This is now the third term. My fourth term be like a politician. In my fourth term, a successful politician if he's 4 terms. Anyway, where were we? Sketching a Bode plot. Fourth term starts at 10 and ends at 1,000. So we start here at 10 and we end at 1,000, and it's down. So we now have this due to the fourth term. Now's the fun part, is putting all of these pieces together. And this one's actually fairly easy because my 0 and pole are not overlapping in their region of slopes. So one's going to turn on, turn off, the other one's going to turn on, turn off. Sometimes you have one on, the next one on, the first one off, the second one off. You have to keep track of all of that. Where do I start my phase curve? Again, I go back to a small frequency, in this case, maybe a decade before anything starts breaking, and I say, okay, what's my phase at that point and before? It's minus 90. And then I keep going until I hit a slope change. And at that point, I look and I say, oh, I'm going up at 45 degrees per decade, but only for 2 decades. I can't just set it and forget it. This is not an infomercial where you set it and forget. Don't they do that with some of these infomercials where you have a Wedge-O-Matic or a blender or something? You set it and forget it. You can't do that on the phase. You can do it on the magnitude because you can turn on the slope and forget it. Here you have to turn it on and turn it off. In terms of the slope, this is now going up 45 degrees per decade, or 90 degrees over 2, and it now looks like that. And if you added all of those phases up at 1, you would have minus 90 degrees due to the pole at the origin, and you would have plus 90 degrees due to the 0. So those cancel each other out, and you now have effectively 0 degrees phase at 1. Now what do we do? Now we quit sloping, don't we? The 0 leveled off at that point. So now we need to be flat. And then we say, oops, we have another factor coming in, and we need to worry about it turning on and turning off. It turns on, and actually we can just follow it down. And there we are. And that's now our total phase curve. Now I could ask you, what's the slope of the phase curve at high frequencies? What's the slope of the phase curve at high frequencies? The slope is 0. Its value is minus 90. You could say, what's the phase at high frequencies? That's minus 90 degrees. What's the phase at low frequencies? Minus 90. Where did that come from? Where did I get minus 90 degrees at low frequencies? That's your pole at the origin, isn't it? That's always giving you minus 90 degrees for all frequencies, and it's active all the way back to DC. Where's DC on this plot? It doesn't exist, does it? DC, this is a logarithmic scale. You'd have to just keep going and going and going to the left. You'd never reach DC. You'd reach 10 to the minus 50, 10 to the minus 60, 10 to the minus 100. But effectively, you're there, right? Questions on that? Everybody an expert on Bode plots? You need to be. So you should have plenty of napkins in the next few days. You can practice. If somebody asks a question, you can just say, would you like to see a Bode plot of that? Right? Somebody can say, well, what did you just draw? Oh, I just drew a bandpass. What was this filter? Maybe low pass. It has a lot of low frequency gain, doesn't it? It has infinite gain at DC, right? That red curve just keeps going and going up. So you have infinite gain at DC. And in the mid frequencies of, let's say, 0.1 to 100 radians per second, you have how much gain? Between 0.1 and 100, how much gain do you have? I'm hearing a lot of answers. 40 dB. In absolute terms, what's your gain? 100. So now if you put in a value, if you put in a cosine waveform at let's say 10 radians per second, and it had a gain of 2, so you say 2 cosine of 10t, what's the output, sinusoidal steady state? 2 times 100, 200 cosine of 10t. And you can get all of that from the red plot. Is that clear? And if you needed to know the phase contribution, you would go down here and you would say, oh, what's my phase at 100 degrees, or at 100 radians per second? No, I was at 10, wasn't I? But let's say it's now at 100. What's your phase? At 100 radians per second. Minus 45 degrees. So everybody see where you're getting that information. The Bode plot now allows you to answer questions about any sinusoid. And this might be good for Fourier series. Meaning if you now have a periodic waveform, not just a sine or a cosine, if you have a periodic waveform, that's a combination of sines and cosines. You can identify the frequency of that sine and cosine and then go to these plots and say what your magnitude and angle are going to be at that particular frequency. So if you have 5 dominant or main modes in your periodic waveform, you can figure out what your output's going to be from this system. Yes? No? This is where we need to be going. All right, quiz, if there are no questions. That's what you want, right? Right before a break, you want a quiz. So let's see if you can now sketch the Bode plot for the following transfer function. Not the last one, but now here is h of s equaling 100 S over S plus 0.1 S plus 10. Can you sketch that Bode plot? And this is more than a yes or no answer. Well, if you want to say no, I guess you can leave, but might as well take credit for doing some of the work. Everybody get a plot? All right, you need to make sure and produce one of those over break if you haven't produced one yet. What are some observations we can make about this particular transfer function or system before we even start sketching anything? We could ask ourselves some basic questions that would check our Bode plot after it's sketched. For example, I might say, what's the slope of the Bode plot at low frequencies? Just based on that transfer function, can you tell me? Now what you're keying in on are poles and zeros at the origin. If you have no poles and zeros at the origin, if you just have linear and quadratic factors, your slope at low enough frequency should be 0. In this particular case, what do you have? You have a 0 at the origin, and what's that producing for you at low frequencies, at all frequencies? It's upstairs, it's a 0, so it's giving us plus 20 dB per decade all the time, isn't it? So at low frequencies, your slope should be plus 20 dB per decade in magnitude. What's the phase at low frequencies? So we've just said at low frequencies, what's the phase? At low frequencies. Can you tell me? And again, you might be keying in on poles and zeros at the origin. They are always active. They're always on. And you have a 0 at the origin. What's that 0 going to give you? It's upstairs. It's contributing a constant phase for all frequencies, and you told me earlier what the angle of J was. 90 degrees. And it's upstairs, so that's going to be plus 90 degrees at low frequencies. That's your phase. If I now said, what's the behavior of this system at high frequencies? Again, these are ways that you could quickly check your Bode plot to see if you're even close. What's the slope of the magnitude at high frequencies? Can you tell me? By just looking at the transfer function, can you tell me what the slope is going to be at high frequencies? Negative 20 dB per decade. Where did that come from? So you look at your poles, how many you have. You have 2. You compare that with how many zeros you have. You have 1. And I refer to this as your pole zero excess. You have 1 more pole than you have 0. And at high frequencies, this system is going to look like something over S. It's going to look like a single pole. When those 3 things become active, which is what they're going to be at high frequencies, you'll have a pole, that'll give you minus 90. You have a 0, gives you plus 90. Oh, now I'm at 0. Give it another pole. I feel like a cheerleader now. Give me a pole. At high frequencies, it's minus 90, right? Give me a 0. Plus 90. So they've canceled out, right? But then I give you a second pole, and now we have minus 90. What was I asking about, slope or phase? Phase? Slope, both. So what's the phase at high frequencies? I got all confused by cheering. Phase is minus 90, right, at high frequencies. What's the slope at high frequencies? Minus 20 dB per decade. Is that clear? So the high frequency behavior you now know. The slope is now minus 20 dB per decade. That because you have 2 poles and 1 0. You effectively have a pole at high frequencies. And the angle or the phase can be found from that same analysis. If you have just 1 pole, it's going to contribute minus 90 degrees at high frequencies. Now we can sketch this. What frequencies, did you all put it into time constant form to begin with? And the denominator pieces all were cooperating. They canceled each other out to give you 1. So you didn't have to adjust that 100. Maybe it's a poor problem, because then if you do 20 log of 100, you haven't made a mistake, even by neglecting what was happening downstairs. But if you even include what's happening downstairs, you get the same thing. Your constant gain is how much? 40 dB. So now we know that we have, in terms of the constant, we have 20 times the log of 100, which is 2 times 20 log of 10, which is 40 dB for all omega. And if I'm sketching this, and I go over to the bookstore, what log paper or what labels am I going to put on my log paper? What's my smallest frequency? A decade before 0.1, right, at least. So maybe we're now at 10 to the minus 1. 10 to the minus 2, a decade before that. 10 to the minus 1, 1, 10, 100. How much more do I need to go? That's far enough, isn't it? A decade beyond 10 would be 100. And I might want to go a decade beyond that to give me 1,000. So if I was up here and down here. Ooh, that was supposed to be a flat line. This is supposed to be 0 dB. I now know that I'm 40 dB due to the constant. I have a 0 at the origin. That's going to be giving me something like this. Very small at low frequencies and very big at high frequencies. Then I have a pole at point 1. And a pole at 10. And now I just put them together. So that right here at 10 to the minus 2, I have minus 40 and plus 40. I'm going to be at 0. And I'm going up 20 dB per decade until I hit something that changes the slope, which is that first pole, and then my slopes cancel. I'm flat until I reach the next slope change, which is that last pole, and now I'm down 20 dB per decade, and there's my magnitude plot. A bandpass filter is what I've created by that transfer function. Are there questions on that? Did I do it properly? What about the phase? I have the same labels, and these are all supposed to be uniformly distributed across the frequency axis. Where am I starting my phase? It's going to be starting based on that 0 at the origin, and that 0 gives me 90 degrees. So now I'm at 90 degrees, well, until what frequency? Maybe what I should do, I have a pole at point 1, I have a pole right here, and I have another pole there. But all my action occurs a decade before and after those breaks. So I'm going to have something, the phase is going to go down sloping wise there a decade before, and it's going to go up right there. For the other one, maybe I should have done it in a different color. Maybe this is the other pole. It's now going to go down here and up there in terms of slope. And I'm going to start at plus 90. And here I'm going to be down and then flat. Here, well, I'm going to be down and then, whoops, that should be the same. Minus 90 is where I should be ending up. Is that clear? And now I just add all of those pieces and parts. I started at 90. And now what happens? Now I need to go down 90 degrees over 2 decades, and nothing is happening to break up or down between those two, so I can simply connect this point with that point. And this is supposed to be a slope of minus 45 degrees per decade. Once I reach 1, what happens? The pole at point 1 quits contributing slope, but the pole at 10 begins contributing slope, so I keep sloping at that exact same value per decade. So that now this is supposed to be going right there. Once I reach 100, everything quits sloping and I pick up where I said I should be ending. Ooh, that's a pretty ugly curve, but that sloping line is supposed to be the same slope. Questions on that? Do you see how you can check your work? Are we accurate? Where was our phase beginning? At low frequencies. Plus 90. Where was it stopping? Minus 90. And I could ask you, what's the slope change, or when is the phase changing over what frequency region? That would be from 10 to the minus 2 up to 10 to the 2. Can you tell my voice is changing? Is that why everybody's starting to pack up? Any questions?